Welcome to our next lecture in the series on condensed matter theory. In this video I want to talk about phase transitions and more specifically about Landau's theory of phase transitions. And if you think of a material, then its properties are described by the Schrödinger equation and the quantum mechanical wave function. So the microstate is given by the wave function of a system. And if we think, for example, of a gas, then we have the atoms in there, and at finite temperature they have some velocity, such that classically the microstate would be described by the positions and velocities, or position and momenta of your atoms. And in quantum mechanics, the microstate is given by a wave function. Now, if you think of your wave function, we can write down eigenstates. And we know that the eigenstates form stationary solutions. Of course, when you look at a classical gas, then the eigens or atoms are moving around, so that is definitely not a stationary solution. So at finite temperature, we are not an eigenstate. So we basically should say H psi is not E psi. And when you're not in an eigenstate, then you're also definitely not in the ground state. We know this from classical statistical mechanics, where you do not minimize the energy, the total energy or internal energy of a system at finite temperature, because that would be the case where your atoms would not move. But you minimize the Gibbs free energy. And the Gibbs free energy is a function of pressure and temperature, and given as the internal energy plus the pressure times volume minus the temperature times the entropy of the system, whereby U is the internal energy. And the internal energy is equal to the total energy of the system minus two terms. And the first term that you have to subtract is the kinetic energy of the center of mass of the entire system. So if you think of a gas that we have in a container, then you do not look at the kinetic energy that you have because of the movement of the full container, but you look at the kinetic energy that you have because of the movement of the atoms with respect to the center of mass of these atoms. And then we also have to subtract the potential energy. If your container sits at a certain height, then you have a potential energy due to the gravitational forces, or if you put it in an electromagnetic field, you can have potential energies. And we do not consider here in the internal energy the potential energy due to external sources. Then P is the pressure, and V the volume. And of course you have an energy because, well, when you have a certain pressure and a certain volume, you can do work, and that is included in the Gibbs free energy. T is the temperature, and S is the entropy. Now the entropy is related to the number of microstates that you have at a certain temperature and pressure and volume that would realize the same macrostate. So we can write down as K Boltzmann times the logarithm of the number of microstates that we have, and the number of microstates is here the number of microstates that will give you the same macrostate, so the same temperature, pressure and volume. And we can define temperature in principle via the entropy as the derivative of the entropy with respect to energy. Now, we can first of all have a look at an example on how the Gibbs free energy would determine different phases. If you think of your gas and you cool it down, then at some point it might condense into a solid. So at low temperature, we have a solid where the atoms sit in a nice order, and we have a vacuum. At high temperature, we have our gas where the atoms move around. Now the internal energy in a solid is much lower than the internal energy that we have in a gas. Here this is the internal potential energy. Which is low. And here U is the kinetic energy. Which is higher. So if you would minimize your total energy, you would definitely go for the solid. The pressure in our container here is 0. The pressure in an ideal gas is the number of particles times the mass of the particles times the average velocity squared. Divided by 3 times the volume. So again, if you minimize the Gibbs free energy, then you would, for the internal energy and the pressure, rather have a solid than a gas. Now if you look at the entropy in a solid is low. There is only a few ways to organize the atoms on a regular lattice. When you have 2 of them, you define all the others, or the position of all the others. Of course, there is still some degree of freedom, but the degrees of freedom that you have at high temperature is much larger. You have many ways to arrange the atoms, where you can slow one down, speed one a bit up, change all the positions. So the entropy becomes much larger. There are many more ways to realize your system in a gas than in a solid. And therefore, basically on the principle that each possible microstate will be realized with equal probability, you come to the conclusion that the Gibbs free energy has to be minimized, and then you will find that there is a phase transition. At low temperatures you would prefer the solid, where the internal energy and the pressure is minimized. At high temperatures the last term at some point takes over, and you would maximize the entropy. You maximize the number of ways in which you can distribute the energy over the internal degrees of freedom. Now if you look at in between, we can have, of course, some atoms in the solid and some atoms in the gas. And for all temperatures we look at the Gibbs free energy and we choose a combination where the Gibbs free energy is minimal. I already wanted to write down a derivative of the Gibbs free energy, but we have not discussed yet to what we should derive. Of course, I know that when the Gibbs free energy is minimal, it must be a stationary state of some variable, and that's actually what Landau used. So the question that Landau asked himself is, how can we apply this to phase transitions? And if you would need to know all the microscopic interactions and solve the microscopic problem, that would be nearly impossible. So what Landau proposed to do instead is to say, well, our Gibbs free energy is going to be a function of some order parameter. For example, how many atoms are in the solid and how many atoms are in the gas phase. And then, of course, the condition that the Gibbs free energy needs to be minimal can be written as the derivative with respect to the order parameter of the Gibbs free energy has to be 0. Of course, that still could be a maximum or a minimum, but then at least we know the stationary states of the Gibbs free energy with respect to the order parameter. Now let's have a look at some examples of order parameter. We can, for example, look at magnetic phase transitions. We have a lattice, and each side we have some spin, some small magnetic moment, and at high temperatures that magnetic moment can be completely random or actually rotate in time, and at low temperature we can have some order, and let's choose an antiferromagnetic order where the different sides, the magnetic moment, alternate between up, down, up, down, up, down. We can now define our order parameter, which is temperature dependent, as the expectation value of the spin operator at side 2i minus the spin operator at side 2i plus 1. And because the local magnetic moment is a vector, so let's take the norm of that vector to get a number. If the orientation is random, then the sum over the expectation values for all odd sides will just average to 0, and the same is true for the even sides. Whereas when we have antiferromagnetic order, the even sides are all up, the odd sides are all down. Then the minus sign makes sure that you subtract a half minus a half for spin a half systems, and you have something finite. Well, we can also look, for example, at lattice distortions. Where we can say, well, at high temperature we are cubic, and at low temperatures we are orthorhombic. Let me make the plot in 2 instead of 3 dimensions. So at high temperatures we have a square lattice, and at low temperatures there is some parallelogram that defines the lattice. And then this angle we could, for example, take to be theta. And theta is 0 in the high temperature phase and non-zero in the low temperature phase. So then this angle that we have in our lattice can be our order parameter. Well, and for the transition between a solid and gas, we can look at the number of atoms that you have in the solid or gas phase, the density at a certain k vector if you want to look at the order that you have in a lattice. So by that way we can define different order parameters for the different phase transitions that we have. Now, in order to make a theory that can describe phase transitions, we then want to take the derivative of the Gibbs free energy with respect to this order parameter to see when we are in the minimum of the Gibbs free energy. We can do this by making a Taylor series in the order parameter. So our Gibbs free energy is going to be alpha 0 plus alpha 2, theta square, alpha 4, theta to the 4th, alpha 6, theta to the 6th, etc. Now you see that I only allow the even orders in my expansion. And actually, if you look at these 2 examples, when I have a phase transition from a cubic phase to an orthorhombic phase, then I can either make a phase transition where my lattice slants to the right, or I can make a phase transition where the lattice slants to the left. Well, if you just turn yourself around and look at the other side of the crystal, both cases must be equivalent. So both energies must be equivalent, both must be equal possible, because you start from a symmetric case and you really don't have a preference to distort in one or the other direction. And when these are equal probable, then it means that the sign of theta doesn't matter, so I'm only allowed to have the even terms of the expansion. The same is true for magnetism. If I have a lattice up, down, up, or a lattice down, up, down, they should be equivalent. This results in the case that when I have a big crystal at high temperature and you cool down, then locally you will pick theta to be either positive or negative. So locally you will distort in one direction, but far away you might nucleate in a different sign of theta, and there you might slide the lattice into the other direction. The same for the antiferromagnet, you might either have up, down, or down, up. And you do not have to condense your entire lattice at the same time in the same domain, but you might find some parts of the lattice that are in one domain and the other in the other domain. So this gives rise to domains in the ordered phase. Now, when we want to make such an expansion and make it useful, we have to truncate at some point our expansion. And in the high temperature phase, we see that the order parameter, the way I defined it, is 0. And you can of course always subtract some constant such that the order parameter in the high temperature phase is constant and 0. And in that case you can say, well, the higher order terms are going to be less and less important, such that we can truncate. Now, when we truncate, for example, after the 6th order, and alpha 6 were negative, then the bigger theta becomes, the smaller the Gibbs free energy is. Which means that you have the minima at theta is plus minus infinite. That would not be a nice definition. So the last important expansion coefficient has to be larger than 0. So we can either have the case where we take alpha 6 larger than 0 and neglect all higher terms, or we can take the case where alpha 4 is larger than 0 and neglect all higher terms. And these two cases we will discuss separately, and one will give rise to first order phase transitions and the other one give rise to second order phase transitions. We'll start with the case of second order phase transitions where we take alpha 4 larger than 0 and neglect all higher order expansion terms. For the case where alpha 4 is larger than 0 and we can neglect all higher order terms, we will get a second order phase transition. And why we will call this the second order phase transition will be clear when we have derived our equations. So we take alpha 4 to be larger than 0. And with that we now want to take alpha 2 such that at low temperatures we'll find the minimum in the Gibbs free energy at the finite value of theta, and at high temperatures we will find the minimum of the Gibbs free energy at 0 theta. So let's have a look what we need to do and how we need to take alpha 2 and alpha 4. So for large theta, we will find that alpha 4 determines G. Because theta is large, so theta to the fourth is more important than theta squared. In this case, when we look at G as a function of theta, for alpha 4 smaller than 0, we will find that the Gibbs free energy goes to minus infinite, whereas for alpha 4 larger than 0, we have the case that the Gibbs free energy goes to infinite and the minimum will be somewhere for finite values. So that's why we have to take alpha 4 larger than 0. Now, close to 0, it is theta squared that determines your wave function. A small number to the power 4 is smaller than a small number to the power 2. So for small values of theta, we can have alpha 2 larger than 0, in which case you have a parabola, and we can have alpha 2 smaller than 0, in which case you still have a parabola, but now with the opposite slope. So if we now connect our function for small values of theta to the function for large values of theta, you will find that because alpha 4 has to be bigger than 0, this will go up and just continue to go up, whereas when alpha 2 is smaller than 0, close to theta 0, you have the negative curvature, but then when you go to large values of theta, you have to go up so that you have a minimum at finite theta. So we can guess that depending on the sign of alpha 2, you either have a minimum at 0 or a minimum at finite theta. So for our Gibbs free energy, we can take the expansion alpha 0 plus, and now I want to have a function that is negative for t larger than tc and positive for t smaller than tc, whereby tc is the ordering temperature, plus alpha 4 theta 4 with alpha 4 larger than 0. So for t larger than tc, we have alpha 2 larger than 0, and our Gibbs free energy as a function of the order parameter has its minimum at theta is equal 0. Or for t smaller than tc, we have alpha 2 smaller than 0, such that our Gibbs free energy has a local maximum at theta equals to 0, and finite theta gives the minimum of the Gibbs free energy. Now at the temperature equal to the transition temperature, you will find that you have a shallow minimum at theta equal to 0. So now we can solve at which theta as a function of temperature the Gibbs free energy is minimum. You just take the derivative and you ask where that is minimum. You'll find that theta is 0 is always an extremum, but it must not be the local minimum, it can also be a local maximum. And if you look at theta minimum as a function of temperature, then above Tc it is minimum, and below Tc it will rise, and theta min is proportional to the square root of T minus Tc divided by 2 alpha 4. And this is a second order phase transition temperature. The order parameter self is continuous, but its derivative diverges at the phase transition temperature. As the Gibbs free energy depends quadratic on the order parameter, we find that only the second order derivative of the Gibbs free energy is discontinuous, and hence we call it a second order phase transition. Now let's have a look at first order phase transitions, where the order parameter itself is discontinuous and makes a jump, such that the first order derivative of the Gibbs free energy is discontinuous. So for the case of first order phase transitions, we can look at, for example, a lattice transformation where you would jump from a cubic to a triangular kind of lattice. An f.c.c. to b.c.c. lattice transformation that you, for example, have in iron would fall under this. So we go from a cubic lattice, and again I just make a drawing in 2 dimensions instead of 3 dimensions in the high temperature phase, to the case where we have a triangular lattice, where we have a finite theta, and theta is 30 degrees. And if you would draw in the additional lines, then you see that this gives rise to a triangular lattice. So you can make this by taking your cubic lattice and slanting it by exactly 30 degrees. So we now want to have a phase transition whereby theta is not some smooth function of the temperature, but is 0 at high temperature, and then at some phase transition temperature jumps, and then is 30 and becomes constant again. So we can do this, and for this we need to take alpha 4 to be smaller than 0. Now when alpha 4 is smaller than 0, as we saw before, then the Gibbs free energy would go to minus infinite when theta goes to infinite, unless we say that alpha 6 is important. So in this case we need alpha 6 to be larger than 0. And we need to include this in the expansion of the Gibbs free energy. So for our Gibbs free energy, we will take alpha 0 plus alpha 2, and we've seen before that when we take alpha 2 to be T minus Tc, that allows us to describe phase transition temperatures. And now we will take it T minus T0, because what will turn out that the T0 is not exactly the phase transition temperature that we have. But at least we will find that when T is smaller than T0, we have a local maximum at 0. When T is smaller than T0, we have a local minimum at 0. So this will give at least the correct behavior in terms of local maxima and minima that we need in our Gibbs free energy. then we have an alpha 4 theta to the fourth plus alpha 6 theta 6. And alpha 6 is larger than 0. So for theta very small, it is theta squared that determines G. So if we look at G as a function of theta, then for alpha 2 larger than 0, we must have a local minima. And for alpha 2 smaller than 0, we have around theta is 0, a local maximum. Now I do know that alpha 6 is larger than 0, so I do have the behavior that it goes up there. And in between, well, we have to connect them in some way. So this is roughly how your Gibbs free energy should look like for alpha 2 larger or smaller than 0. Now at Tc, we want our Gibbs free energy should be minimal for theta is 0 and theta is plus minus 30. And we still can't determine if you slant to the right or to the left. So we want our Gibbs free energy to have a form where your minimum at 30, your minimum at 0, and your minimum at 30 degrees again. Then when temperature is increased, you want the local minima at 30 to move up. So at higher temperature we want the Gibbs free energy to look something like this. And when the Gibbs free energy, when the temperature is smaller than Tc, we want the global minima to be at 30. So there we want the Gibbs free energy to have a look like this. And of course the exact form that we have and where if you have a local minima or not at 0 is still open, and we should have a look at that. Now let's have a look how we can implement something like this that would give you a phase transition where the local minima jumps from 0 to 30. So we want to have a look at the case where the derivative of the Gibbs free energy with respect to our ordered parameter is 0. Well, we have our Gibbs free energy as a function of theta. So if we look at its derivative, then we find 2t minus t0 theta plus 4 alpha 4 theta cubed plus 6 alpha 6 theta to the power 5 has to be 0. And there are two solutions of these equations. Either theta is 0 or theta squared is minus alpha to the fourth plus minus the square root alpha 4 squared minus 3t minus t0 alpha 6, and that entirely divided by 3 alpha 6. Now we need to have the derivative of g with respect to theta to be 0. Of course this can be a local maxima or a local minima, and we know that when t is smaller than t0 it's a local maxima, when t is smaller than t0 when t is smaller than t0 it's a local maxima, when t is larger than t0 it's a local minimum. Now, in order to see if we have a second local extremum, local minimum or maximum, we can have a look at this equation. And whenever the value underneath the square root is negative, be sure that we do not have a real solution. So based on the value that we have here, we can make the conclusion that when t is larger than t0 plus alpha 4 squared divided by 3 alpha 6, then there is no real solution at finite theta. Let's define this as temperature T1 is T0 plus alpha 4 squared divided by 3 alpha 6. So we can now define 3 different cases. When the temperature is larger than T1, we only have one solution, and that is theta is 0. When the temperature is in between T0 and T1, we have 2 local minima. Theta is 0 or theta is plus minus the square root minus alpha 4 plus the square root 3 alpha 6 T1 minus T divided by 3 alpha 6. When T is smaller than T0, we have a local maximum at T equals 0, and theta is equal to plus minus alpha 4 plus, again, the square root 3 alpha 6 T1 minus T divided by 3 alpha 6. I did a little bit of simplifications in there to get to T1 and have a slightly nicer expression in here. So we see that we definitely have a phase transition at high temperatures. Theta is 0, so our Gibbs free energy as a function of theta at T larger than T1 has a minimum at 0. At low temperatures, T smaller than T0, we will find the local minima at the finite value of theta, and somewhere in between you will have 3 local minima, T larger than T0 but smaller than T1. So this will result in a jump in your order parameter, where at Tc you have the 2 local minima, and theta as a function of temperature will have a jump at Tc. And then we have here T0 and T1, where in principle you have solutions, but the global minima jumps at Tc, and it is only the local minima that survive above and below. And we can actually derive what Tc is, which is T0 plus 3/4 T1 minus T0. So I shouldn't have drawn it here in the middle, but closer to one side than the other. Now, if you just pick random values for alpha 4 and alpha 6, then theta will be temperature dependent, but you can puzzle and find ways to pick alpha 4 and alpha 6 in such a way that they are not temperature dependent. And when you have a microscopic model where you make a phase transition, where you go from cubic to something that is triangular, then well, you have 2 atoms at different angles you have a different energy, but when you're exactly in the middle, you have the center of the two, so that can very well be a local minima. And then you would find that you just pick alpha 4 and alpha 6, such that you get a temperature independent value of theta below Tc. Now, what we see here actually has more implications. If you are in a low temperature phase, water, and you start to heat, then the Gibbs free energy is going up, but you sit in a local minima, and at some point you can still be in the local minima, but above Tc. It's no longer a global minimum. Nonetheless, you don't have to jump immediately from the local minima to the global minima, and you can have overheated water. If you take pure water in a clean glass and you put it in a microwave, this can actually happen. You can overheat your water, it becomes hotter than 100 degrees Celsius. It should start to boil, but it didn't yet. You're in the local minima, but no longer in the global minimum. If you then take it out and you take a spoon and you hit the glass of water, it all of a sudden starts to violently boil, because, well, then it jumps from the local minima into the global minima. You can also do this in the other direction. If you take a gas and you cool it, then you can cool it below the phase transition temperature. You're still in the gas phase, although you want to condensate. And this is, for example, something that you use in a bubble chamber where you have undercooled gas. And then when a particle comes through it and has an interaction with this gas, it starts to make a condensed trill. So with the use of Landau's theory, we can also explain not only that we have phase transitions, but also that the phase transition, that you can have undercooling, overheating, etc. You now also see why we call this a first order phase transition. In this case, the order parameter is discontinuous at the phase transition temperature. So already the value of the order parameter and not just its first derivative is discontinuous. Now let's recapitulate how within Landau's theory we define phase transitions. And phase transitions in Landau's theory are characterized by an order parameter. Originally, Landau restricted his order parameters to symmetry breaking phases, which are both examples that we have here. The symmetry of the Hamiltonian that you have in the low temperature phase and the high temperature phase is different. But you can be more general in terms of an order parameter, and anything that you can use to describe the phase transition that is discontinuous or is not analytical at the phase transition temperature can be used as an order parameter. So a liquid to gas transition, which have both the same symmetry, you could, for example, do by the local density for your order parameter, which changes at the phase transition temperature. If you think of symmetry, then the order parameter breaks one of the symmetries of the Hamiltonian, describing the high temperature phase, and then the low temperature phase that emerges is of lower symmetry, one of the symmetry operations that commuted with the Hamiltonian is no longer there in the low temperature phase. The low temperature phase is not necessarily an eigenstate of the high temperature phase. If you think of the order that we have for our antiferromagnet, then the antiferromagnetic order is not an eigenstate of the high temperature Hamiltonian, which of course is slightly weird, but that's the way our system works, and this is what we call spontaneous symmetry breaking. You might find low temperature states that break the symmetry of the high temperature phase, and they don't belong to irreducible representations of the high temperature phase. So the nil state is not an eigenstate of all the symmetry operations that we have for the high temperature phase, which is spherical with respect to the symmetries that we have, or to the rotation of the spin that we have. This theory has been extremely successful, and we can use to describe the different phase transitions that we have in materials. You can make... Very nice. You can make Siri. You can make microscopic models, for example, for magnetic order, which you will do later in the lecture or in one of your homework problems, and see that indeed those describe, those get to the same physics, and you get the same kind of behavior in the Gibbs free energy. And with the use of the Gibbs free energy, you can also calculate things like the specific heat of the material or susceptibilities that we have in our system. For today, it's enough to just realize how we can describe these type of phase transitions. Phase transitions break the symmetry of your Hamiltonian in the original Landaus theory, such that the Hamiltonian in the low temperature phase is of lower symmetry than the high temperature phase. The eigenstates of the low temperature Hamiltonian are not necessarily eigenstates of the high temperature Hamiltonian. And that's how we work with these systems, and they describe reality really well. So thank you very much for your attention. Hope to see you in the next video. Stay healthy.